everyone. My name is Andrei Zabavsky. I am Big Data Architect at SoftServe company, and welcome to Azure Cosmos DB conference. Today, I'd like to talk about Cosmos database modeling methodology, which is based on domain-driven design aggregates. So if you're talking about briefly agenda, so first I'd like to talk about motivation, why we need any methodology in general at all. Then I'd like to talk about case study or example we're going to use throughout this topic, and then to talk about methodology itself, first like in the high level, in the nutshell, and then go through each individual modeling steps. So first of all, in my opinion, many people undervalue the importance of the NoSQL database modeling. When we're talking about relational databases, so it is well-known fact that if in using the normalized techniques for the operational OLTP databases, so denormalizing for the analytics, we always are going to have a good query response time and efficiency in general for like any query. But it doesn't work that way for NoSQL. For NoSQL, we need to take into consideration also application workload, queries, and the good model would be just model according to this application workflow, and in such a case, our model will be efficient, or otherwise we can just fail our project. Let's talk about the case study, an example. So actually, a couple of months ago, I was assigned to a project which was intended to migrate a big legacy e-commerce platform to the cloud. Actually, there were a lot of issues with the legacy system, and the important one which I was considering and was working with is a data access layer. So the on-premise database which was implemented with SQL Server was implemented using like dozens of different databases with a lot of interdependencies and a lot of complexity around the schema itself. So, and there were also a couple of other aspects which were so that it was impossible to perform lift and shift migration to the Azure using Azure SQL or managed instance for the SQL Server. So that's why it was made a decision to migrate to Cosmos database. But as I said, it was not trivial and straightforward task because of a really big complexity on the database level. You can see some numbers on the right side. So like more than 300 different relational tables, a lot of stored procedures, and a lot of like backend logic implemented as REST API endpoints. All of that should have been migrated to Cosmos DB. So, and taking into consideration this context, I really required to have clear methodology how exactly to move all this database, data model, tables, and logic to the Cosmos DB. And just a simple suggestion was not enough for me, and I was looking for like a methodology, ground and solid methodology, how to do that. And actually, it was hard for me to find any. That's why I was like working on my own one, and so that just to have this clear guidance how to migrate. And today, actually, it is a topic of this this talk, explaining this new methodology. As an inspiration for that, I used three main sources. So first one is H. Botko's paper for Cassandra data modeling. This is my favorite one because it really gives a clear methodology, clear list of steps how to go from the application workflow and conceptual data model till the end, till the actual physical data model on Cassandra. So it's really cool stuff. But the only issue is that it's for Cassandra. And when we're talking about Cosmos DB, and when I mean the SQL API and document-oriented kind of model, so I cannot apply this approach right away. So it should be definitely changed, adjusted, and tailored for Cosmos DB. And another thing, another source of inspiration was aggregate-oriented domain-driven design practices. You can probably, you heard probably about this splitting the NoSQL storages between aggregate-oriented and other ones. So, for example, Martin Fowler also talking about like 3 types of NoSQL, like key value, document-oriented, and column store-oriented. All of them are aggregate-oriented, and you can consider this aggregate-oriented design while you are preparing your schema. So it's good to know, but also hard to find any details, any exact recommendation how to apply that. So my intention was to research this area and understand for myself how we really can apply that. And turns out it really a lot of useful stuff, and we could use it while preparing the model for Cosmos DB in particular. And the third source of inspiration, definitely a lot of good resources on and suggestions for Cosmos database, like models and structures preparation, which are posted on Microsoft site and other places. So let's talk about methodology, like executive summary or in a nutshell. Here you can see a list of building blocks or steps, what we need to do, going from the very first inputs until the final physical data model. So similarly to the Chobotko approach, first 2 items are conceptual data model, or understanding the whole subject area you are trying to model, and application workflows. These 2 main inputs which we can start from and use to build our data model. The next steps would be preparing the aggregate-oriented domain design. So these rounded boxes are activities we need to do. Then when we have prepared aggregate-oriented domain design, take into consideration also queries and command statistics, as well as data realities. We can map this data model to the logical data model. So logical data model you can treat as a first version of the actual representation of the data on Cosmos database side. And the very last steps would be apply some series of physical optimization so that we can have the final version of the physical data model on Cosmos database implemented. All right, so now let's go through each of the steps and consider an example using the case study I mentioned above from the e-commerce business. So as any data modeling activities, we need to start from the conceptual data model. So we need to explore our subject area and define list of entities and relationships. So here we are talking about mainly structural association. And in terms of reflecting this data model or representation, so we can use different options. We can use either like classical database conceptual data model using different notation, and you can see in this example like Krauss-Foot notation, or we can use also UML class data diagram. So let's consider how the conceptual data model look like, taking into consideration our particular example from the e-commerce business. So in the center, you can see one of the main entity, which is order. Each order contains a list of order items, and it could also contain different list of payments in scope of one order with different payment method and using different credit cards. One order could contain many packages with different shipping methods. Each order also has some order status history, and each order is bound to a particular account. So account means like particular customer or client. And if you're talking about customer, a lot of different information related to account, like it's addresses, credit cards, bank accounts, contact information. And also what is important is any e-commerce business is selling some goods or products or items. So we have each order item is bound to some product item. And each product item is stored in some warehouse. So we're also interested in item availability here in different warehouses. And since the e-commerce platform is multinational, we have different websites in different countries. So we have different representation of the same product in different countries, which could be also served in different sizes, variants, and options. So that's briefly it about our data domain. We're going to model which is extracted from the real world scenario. The second step would be application workflow. So here we mean the actual data lifecycle, how the objects are created, updated, deleted, how the objects are queried. So what are the data retrieval patterns? And here we also important to understand what are the parameters for each query, what we are querying by, and how the results are represented. So here, I don't want to go through, like if you're talking about our case study, so I don't want to go through each particular query, but just to give you a couple of examples here, you can see a query structured in different categories. So it's like display product specific, product item specific, account specific, and order specific. So, and you can see like just to name a couple of examples. So for example, if you're talking about contact account, we need to create account, we need to create bank accounts, like save and retrieve, work with different aspects for ordering, like put in new order, change status, retrieve status history, create packages, etc., etc. So where we are right now, we discussed conceptual data models and application workflows, two main inputs. And the next step would be to create aggregate-oriented domain design. So how to do that? So it's pretty big topic, and you can read a lot of good resources. For example, Eric Evans' book. It's one of the first and best one. But just to go through it really briefly. So domain-driven design aggregates, how we prepare them. So first of all, we need to distinguish between two types of objects. First is entity, and second one is value objects. So entities are objects defined primarily by their identities. So for example, if you're talking about some particular person, so it has its own identity. So for example, if this girl change the haircut or anything else, it remains the same girl. While value objects are not, for them, it's not important the identity, because they represent list of descriptive aspects. So for example, colors or materials. So it's not important the actual identity of this green color, but it's important the value of its attribute. So then when we split our entities between our subject area between entities and value objects, we can start thinking about aggregates. So aggregates, it's a unit cluster of entities and value objects bound together in a unit for data changes. Each aggregate also has its own one entity is defined as root of aggregate, and the other one, it's just not root entities. And root aggregate entity has kind of global identity, while not root entities are just local identities and could be referred only inside the aggregate. So let's review how for our case study how we can split our entities between set of different aggregates. You can see here on this drawing, on this diagram, split the whole subject area into a set of different aggregates. And here you can see each aggregate. So for example, account aggregate has its own root entity, list of non-root entities, and this stippled boxes represented the value objects. You can see that for account, we designed credit card, bank account, contacts, we treat as non-root entities. Main address, ship address, contact types are value objects. And similarly, you can review also other aggregates. So for example, orders has like payments or their histories. These ones are non-anchor entities and list of value objects, and also other aggregates. So in such a case, we prepared this DDD aggregates. Let's move forward. The next step would be understanding the data realities and query statistics. So that's really important for any data model, but in particular for NoSQL. So we need to understand like what are expected data volumes, what is cardinality of different attributes, and what one of the most important, what is relationship nature. I mean, one-to-one, one-to-few, one-to-many. And in terms of data workloads, it's also very important to understand whether we have write-heavy application or read-heavy. So would be really good to have this statistics gathered. And if we build something from scratch, not migrating existing application, we need to understand at least at the level, like order of magnitude level, what use cases and scenarios we're going to have, what kind of queries are going to be more popular and less popular. All right, so we covered this list of steps. And now one of the most important and interesting part is how to map those aggregates to the actual data structures already on Cosmos database. And I prepared for that a list of rules. So let's review them briefly. All right, so first rule is each aggregate map to one Cosmos DB container. Then primary key of anchor entity defines the partition key of the container. The third rule is that each non-anchor entity inside the aggregate is mapped to just separate document type inside the same container. And we will take a look at the examples slightly later. The fourth rule is talking about how to map value objects. And here there are two possible options here. So first one is actually it works in majority of cases. Value objects are going to be embedded into the appropriate parent document type as a embedded JSON objects. It's a first option, and another option is just could be treated as separate document type inside the same container. So option one we use in case we have one-to-many or one-to-few relationship type and infrequent changes inside these attributes. And otherwise we just going for option number two. And the last two rules for mapping is mapping rule number 5 is related to dictionary containers. So we need to have inside, if you're talking about real big and complex data domain, usually we have list of dictionaries we need to use. And we don't actually need to have separate container for each individual dictionary, so we can join them together in one specially dedicated container for dictionaries. So we can take as a set of aggregates which consist of just one orphan anchor entity and map them to different document type inside special dedicated dictionary containers. And the last rule is talking about inter-aggregate relationship. So for this particular case, we can just use a referencing technique and not embed the whole like child document, but just store and ID reference for that. So applying all these mapping rules, we came across to the first logical data model on Cosmos DB site. You can see here that we defined a list of the following containers, like account container, order, display product, and product item, and especially dedicated dictionary containers. Each containers has a partition key defined by anchor entity primary key. So for example, we can see we have product ID for product container, account ID for account, and etc. And similarly to other containers. Inside each container, you can see a list of different document types, like account, credit card, bank account, and contact. All of them are just different JSON documents which share the same partition key. And I use this particular notation to show that these parts of the entities are embedded JSON documents. So we embed like ship address and main address inside the account document type, inside JSON with account. Similarly, contact type we embed into contact. And the last piece, you can see this dashed arrow. It's like referencing relationships. So inside display product, we can just store the country ID. So in such a case, you can see how we came to the logical data model. Now we are really close to the end and would like to concentrate on the last piece, which is like physical optimization. What does it mean? When we're talking about physical optimization, you can apply different techniques and consider different aspects. So first of all is like reviewing the sizes of the partitioning, just tracking whether we don't have like too big or too small partitions, and how our data is being distributed. The next topic, important one, is about index strategy. So default one, it's not always good for our design, and we need always to balance between putting more indexes and optimize different read operations versus less indexes to optimize writes, right? The third important item would be a possibility to duplicate data set, the same data set into different containers. So, and especially that is important for when we have cross-partition queries which are not well served by the index. In such a case, we would need to duplicate this into another container so that the appropriate queries will use partition key. And the last one, we like reviewing possibility to introduce counters to avoid aggregated queries. Applying these techniques to our particular use case, what we can do. For one, a big thing we made here, we just duplicated the orders information to account containers. So that allow us to query different orders by account ID. And we don't need to do cross-partition queries for like all the orders by particular account. Another small improvement, since country information is not really changes, almost never changes, we can embed country inside the appropriate parent documents. Yeah, so that's briefly it about different modeling techniques. I'd like to thank you for attention and invite you to search through my blog post as well as services provided by SoftServe company. Thank you.